Magnetars. I guess you can already start sharing your screen. Let's see.
Thank you, Professor. Can you hear me?
Yes, perfect.
Okay, now you see.
You do see?
Do you see the slide?
Yeah.
Okay. Thank you, Professor. Hello, everyone. My name is Danjela SERİM, and I'm currently a researcher at Middle East Technical University. Today, I'm going to talk about the timing noise properties, and we have also added to this the timing noise of persistent accretion pulsars. And my presentation, as it is shown, is entitled as the pulse frequency noise of magnetars. Here is the outline. Since Professor Ersin already explained very many properties of magnetars, I'll very briefly explain only the main characteristics of magnetars which are related to the results of this work, and also the two main models which explain the mechanisms of magnetars, and directly jump into the methodology, data, results, and the conclusion. The aim of this work is to understand and reveal the timing noise processes that governs the pulse frequency fluctuations in magnetars. In order to reach this goal, depending on the sampling data, we first investigated the power density spectra of each source in different time scales. Afterwards, the timing noise strength for similar time span of approximately 1,000 days is used to investigate any possible correlation between timing noise and other physical parameters, such as magnetic field, spin down rate, X-ray luminosity, and the characteristic age. By doing so, we try to associate or investigate how timing noise is related for different pulsar groups, such as magnetars, radio pulsars, and persistent accretion powered pulsars. We have investigated the noise strength of the study sources via two methods, which namely RMS value method and delta 8 method. The general characteristics of the study sources in these presentations are as follows. As I mentioned earlier, for comparison, we have also investigated the sample of persistent accretion powered pulsars. Therefore, they will also be introduced very briefly here. To begin with, the most distinguishable characteristic between these two categories are that magnetars are isolated sources, while persistent accretion powered pulsars, from their name, reside in binary systems, which means that they can accrete accrete material from their companions. Regarding their magnetic fields, magnetars have inferred dipole magnetic field strength values of the order of 10 to 13 to 10 to 15, which makes them actually the objects with the highest magnetic field values in the universe as we know it. While the magnetic field strength values of accretion pulsars are of the order of 10 to 12, at least the sample that we have studied here. The estimated spin down period of magnetars are between 1 to 12 seconds, while the spin period of the persistent accreting pulsars studied in this work ranges from 1 to 700 seconds. Magnetars are always found to be spinning down, just like radio pulsars, while accretion powered pulsars are observed to have episodic spin-ups and spin-downs, depending on the sign of their torque coming from the accretion. Therefore, magnetars are thought to be empowered by either magnetic braking, just like other isolated pulsars, or from Derby's disk, while the accretion pulsars, from their name, are powered by the accretion. Here is a table with the main characteristics of pulsars of magnetars, I'm sorry, actually that is taken from the literature, but I only present it to you because these are the characteristics that will be used to investigate the noise of magnetars and the correlation between these parameters. As can be seen, the period of magnetars ranges from 1 to 12 seconds, and the P dot values are in here, magnetic field values, and the X-ray luminosities. Why? Okay. While here is the table of the persistent accreting powered pulsars that we have studied here, and their main characteristics, such as the class they belong to, the orbital period, the spin period, the magnetic field, and their X-ray luminosities. Before going to the investigation of the timing noise strength of magnetars, I'll very briefly try to explain two main models that describe the characteristics, the observed characteristics of magnetars. And the name and the two main models are called the magnetar model and the fallback disk model. Magnetar model, in principle, assumes that magnetars are sources with enormous magnetic field strengths beyond the so-called quantum critical level, and it is precisely these magnetic fields which are responsible for the observable characteristics such as burst, outburst, flares, and their X-ray luminosities. This model, however, cannot count for the period clustering of magnetars and also for their optical and infrared emission detected in several magnetars. On the other hand, fallback disk model claims that the magnetars are surrounded by a leftover disk from their supernovas, and this disk is responsible for the observed characteristic. Fallback disk model does not require extreme magnetic field values, but rather their strengths are of the order of 10 to 12 Gauss. This model can count for the period clustering and the optical infrared emission observed in magnetars. However, its biggest breakdown, we may say, it is the disability to count for the radiative behavior magnetars are characterized by. Without entering into too much details, it can be said that the timing noise of pulsars is the study of their rotational, astrometric, and binary parameters. Timing noise analysis is very much depending on the data sampling rates of the source. That is, the more frequently and continuously a source is observed, the better we can understand its timing behavior. Therefore, in this work, in order to accumulate as much data point as possible, we have gathered as many observations as possible. For magnetars, we have used the data of XMM, Newton, Swift, Chandra, and RXT X-ray observatories. And with the obtained data, we have either reconstructed a given solution or we have used the frequencies found in the literature, depending on the data, as I said. While the obtained note that these frequency histories are used to estimate the timing noise strength of each individual source. All the data are glitch-free intervals, since glitches are known to contribute as a misleading excess noise. And out of 24 magnetars, three of them have no data to conduct measurements of any kind, and 3 more are already studied in the literature. On the other hand, for accretion-powered pulsars, the work was relatively easy because the frequency history of these sources are directly used from the Fermi GBM pulsar project and BATSE GRL pulsar project. And out of 8 accretion-powered accretion power pulsars. Two of them are already studied in the literature, and the remaining 6 will be studied in here. The following slides show the frequency histories of each individual source. As can be seen from here, the ones that have horizontal error bars means that they are reconstructed using the timing solutions found in the literature, while the figures like this one, for example, which do not have horizontal error bars, means that they are composed of frequencies found in the literature. And since there are 18 Magnetars sources, these are the frequency histories of other sources which are, as I said, either reconstructed or found in the literature. I'll pass them fast because there is no any specific thing to say about them. And here is the frequencies, is shown the frequency histories of accreting pulsars. And as it can be seen, these sources have episodic spin up and spin down intervals. And something to notice are that accretion power pulsars are studied are observed very frequently, and their data span spans for almost 10,000 days. Now that we covered the frequency histories of the Magnetars, we can jump into the what we call timing noise strength analysis. Once the frequency histories are settled, we can proceed with the constructed power density spectra and their representative timing noise values. To achieve this goal, let us first have a look at the theory behind it. In principle, timing noise is called the stochastic wandering of time of arrivals after modeling those time of arrivals with an appropriate model. The noise strength is calculated and interpreted in different ways depending on the approach. Over the years, timing noise strength of pulsars is estimated via Bayesian approach method, which is the newest one, which is used for measuring the timing noise strength of the pulsars, the RMS, or as we call it, the Dieter method, and the delta 8 method. In this work, we have studied only the we have measured the timing noise of our studied sources with only the RMS value method and delta 8 method. The most widely known methodology for measuring the timing noise strength of pulsars, which is also the one used in the calculations of this work, is the one put forward by Boyton et al. And later enhanced by Dieter. Fundamentally, this method uses the root mean square values of the timing residuals for interpreting the timing noise strength level. Hence, upon describing the pulse frequency evolutions with a polynomial of order m over a time spin t, we obtain the residuals. Then we measure the RMS fluctuations of these residuals to calculate the noise strength, which is shown in here, for the time scale t. These fluctuations depend on at least 2 parameters. The order of the polynomial, because as it can be imagined, depending on the model, the residuals will change, and the value of the time span of the data. Observed fluctuations in the residuals then can interpret it as random walks in phase, frequency, or spin down rate. Here, R is the order of the red noise. Sigma stands for the root mean square values of the residuals. SR, as I mentioned, is the timing noise strength in the time scale T. And this parameter in here is called the normalization factor of the timing noise in unit time scale. The other On the other hand, delta 8 method calculates the noise strength using the mu and mu double dot values of a pulsar for a fixed time interval. Note that the time span of 10 to 8 in here has no specific purpose, but rather is the average time interval of the observations of the sources calculated. This approach is very model dependent. However, several papers have shown that, that this method gives a rough estimate of the timing noise of isolated pulsars. What we have done with our data and with the frequency histories that I already shown is as follows. For Magnetars, an investigation of the residuals of pulse frequency indicates that they can be characterized by a first order red noise. The regular rotation evolution of accretion part pulsar are represented in terms of a second order degree polynomial, and the remaining pulse frequency residuals are examined for the pulse frequency fluctuations. Afterwards, the timing noise amplitude are performed for the maximum timescale t of the available data. Depending upon the sampling rate of the data, calculations are iterated for smaller time scales, such as firstly we measure the timing noise strength for the maximum time span of the data, and after them we repeat the calculations for t to the 2, t to the 4, and so on until the smallest time scale for polynomial fitting or measurement noise level is reached. For each time scale, the timing noise amplitude estimations are logarithmically bin and accumulated into one single power density spectra. Something to notice is that we call the white noise the distribution of the power of fluctuation, which is time span dependent, and we call independent, and the red noise the distribution of the power of fluctuations, which is time span dependent. The upcoming several slides consist of the constructed power density spectra of the studied sources. I have tried to group the power density spectra of magnetars, however, their patterns are rather inconclusive. This slide consists of power density spectra of magnetars possessing a white noise. However, SGR J1745 and 1E1567 have a reddish point at their longest time scales. This may imply that a red noise formation at longer time scales, therefore more data are needed for a better understanding of their timing noise behavior. This group of magnetars power density spectra consists of magnetars which are characterized by a red noise power density spectra. By red noise, as I mentioned earlier, we mean that their timing noise strength values is dependent to the time span which they are measured. This group of power density spectra of magnetars is characterized by a steep red noise component in the longest time scale and the flatter structure of instrumental noise in the shorter time scales. By instrumental noise, we mean that their power density spectra, their noise strength estimation go alongside with the instrumental noises. And here is the last group of power density spectra of magnetars, which are characterized almost completely by their instrumental noise, that is their power density spectra. Their noise strength estimations go alongside with their instrumental noise. Here is a table of all the studied magnetars with their characteristics. I have tried to put them in one table. That is, here is their noise strength estimation for a time span of what is shown in here, and their noise type, whether they are white or instrumental noise or red, and their power law indices and the frequency range of these power law indices. And here at the end is shown their delta A measurement values, which I will not show in here because the calculations are straightforward. We just model the data and then find the result and use it for our correlations. Now we can move on with the timing noise spectra of the accretion powered pulsars. As seen from the figure, here is the power density spectra of Vela X1 and Genk X3, Centaurus X3. Vela X1 is characterized by a white. By white, we mean that the noise estimated are evenly distributed over the time. And while the power density spectra of the Centaurus X3 is characterized by a red noise component. For accreting systems, white noise structure is expected from a pulsar accreting via wind accretion, while red noise structure is expected from a pulsar which accretes via disk accretion. And our constructed power density spectra are one-to-one consistent with the general characteristics of the studied sources. Here it is shown the power density spectra of Hercules X1 and GX 301-2. And here is the power density spectra of the last two studied persistent accretion power pulsars. Same as Magnetars, here is a table which shows the characteristics of their timing noise of the accretion powered pulsars with their name, their noise strength values for a time span of approximately 1,000 days, and I will explain in a minute why we have used the time span to 1,000 days. The noise type, whether is it white or red or instrumental noise, their power law indices, and their I'm sorry, the last figure I cannot, and their frequency range for the measured power law indices. Okay, once we have investigated the timing noise strength of each individual source on different time scale, now we can move on with the noise correlations. Here, a systematic cross-examination is performed to reveal possible correlations of the timing noise strength with the physical parameters, such as spin down rate, magnetic field, X-ray luminosity, characteristic age. And the idea is that to understand the physical mechanism that produces the fluctuations observed in spin frequency evolutions of pulsars. In order to make a meaningful comparison for timing noise strength amplitudes on different sources, they should be examined in a similar time scale because, as I said, measuring the timing noise strength of a source is time span dependent. For each pulsar or magnetar, the power density estimation of on a time scale of approximately 1,000 days is selected for comparison. This time scale preference is favored since the time span of delta 8 calculations is also approximately 1,000 days. That is 10 to the 8 seconds is almost 1,150 days. On the other, however, some magnetars have not enough data points to estimate the timing noise strength for 1,000 days. If this is the case, the noise strength corresponding to the maximum time span of the data is used for comparison. On the other hand, accretion powered pulsar sample is examined only via RMS value method because preliminary analysis showed that the mu double dot values do not constitute a reliable metric for timing noise analysis due to their drastic variability over relatively short time scales. To build a more comprehensive picture on the noise behavior at broader range, of pulsars, a sample of radio pulsars are also added to the correlation studies. To enable such a comparison between the timing noise behavior of our target sources with radio pulsars, we converted the reported RMS values of 366 pulsars found in the Hobbs et al. 2010 to the noise strength values using the corresponding normalization factors. Okay. Initially, the connection between the magnetic field and the noise strength of pulsars is examined via both methods, RMS and delta 8 method. In the magnetic field versus timing noise strength, magnetars are located in the upper right region with their immersed magnetic fields and the high levels of timing noise. The pulsars are correlatively distributed to the bottom owing to their moderate magnetic field strengths and rather low timing noise levels. We attribute these relatively high noise strength values to the variations in the magnetospheric moment of inertia of isolated pulsars and magnetars. On the other hand, a accreting pulsar sample is located in the upper mid, in here, in the upper mid region of the diagram with their high level of timing noise originating from accretion torques. The narrow clump of accretion powered pulsars in here can be associated with the magnetic field measurement techniques that is used in accreting pulsars. PAPs seem to have a higher level of timing noise compared to the radio pulsars, and obviously inhomogeneities in accretion flow increases the fluctuation in torque extended to the pulsars, and the measurement timing noise strength scales up accordingly. As can be seen from this figure, here the delta 8 is used only for magnetars and not for accretion powered pulsars, because preliminary work, as I explained, showed that the delta 8 method cannot represent the binary systems. Here is the other correlation that we have examined so far. In this particular section, only 3 accretion powered pulsars are included in the correlation figure because spin down because the noise strength estimation of 1,000 days scale of each here only 3 accretion powered pulsars are investigated because, as I said, in order to have a meaningful comparison between the timing noise of different sources, we have to choose a time span of a similar time span, and we chose it time span of 1,000 days. So there are only 3 accretion powered pulsars which have a long time span of approximately 1,000 days. That's why we have used only 3 accretion powered pulsars in this particular section. As can be seen from here, the timing noise strength of magnetars seems to have a correlated behavior in the graph of the mu dot versus timing noise strength, and accretion powered pulsars are in the case of mu dot versus timing noise for both RMS and delta 8 method, the level of timing noise of magnetars is relatively higher than that of the radio pulsars. Magnetars seems to exhibit a correlation that corresponds to radio pulsars. However, the level of timing noise of magnetars is significantly higher from the pulsars within similar mu dot range. When the P dot versus SR and delta 8 diagram is inspected closely, all the sources seem to exhibit a correlative behavior and form a overall continuum, as is seen in here. On the other hand, the timing noise timing noise values of accretion power pulsars resemble those of magnetars, and they also seem to have a correlative behavior in a similar fashion. However, more sources with similar characteristics should be added in order to have a more comprehensive understanding of the behavior of timing noise versus spin down rate of the accreting pulsars. The next investigated relation is the timing noise strength versus X-ray luminosity. For magnetars, the luminosities are not defined as a range, since their quiescent luminosity level is rather stable, and unfortunately, outburst changes their luminosities for several orders in magnitude. For persistent accretion power pulsars, the X-ray luminosities reported in literature is gathered, and the range from maximum to minimum level of X-ray luminosities are included for comparison. Similar to the previous sections, two diagrams for SR and delta 8 versus X-ray luminosity is constructed. In both cases, magnetars are distributed randomly over the diagram, indicating that there is no connection between timing noise level and X-ray luminosity for magnetars. On the other hand, persistent accretion power pulsars exhibit a correlative behavior in the SR versus X-ray diagram. This is in argument with the studies in literature from Baikal et al. 1993, when they also found a correlation between the X-ray luminosity versus timing noise strength of accreting pulsars. This is in agreement also with the study of Kort et al. When they studied the timing noise strength of 50 isolated pulsars, and they found no correlation between the X-ray luminosity of those pulsars and their timing noise strength.
Danjela, we are eating from the break, so I'm gonna have to ask you to maybe conclude in a few minutes. Okay?
Okay. Okay, only 3 more slides, Professor. The other correlation is between the characteristic age versus timing noise strength, and here the accretion power pulsars are excluded because we do not have exact measurement of their characteristic age due to their accretive nature. As from here we can say that there is an anti-correlation between the characteristic age of magnetars and their timing noise strength values, and they form a continuum with the radio pulsars, and from here it can be inferred that since the magnetars we know that magnetars are younger sources compared to the radio pulsars, it can be said that the younger the pulsar is, the more noisier it is, and as the time passes by, their noises also step down, and the other source is that as a last correlation in this work is that since the correlation shows that the magnetic field correlates with the timing noise strength, and since the magnetar models predict that the magnetic field is responsible for the radiative behavior of magnetars, we further investigated the relation between the timing noise strength and the total outburst energies reported in the paper of the Zelati et al. 2018 and references therein. From these figures, it is clearly shown that there is a correlation behavior between the timing noise and the total outburst energies of magnetars. Here, the green represent the sources which have had 2 outburst episodes. Zelati et al. Also showed that the magnetic field of magnetars is correlated with their outburst energies. Therefore, we conclude that the timing noise behavior of magnetars is related to its magnetic field, and that the magnetar model is a more plausible scenario representing the behavior of magnetars, by keeping in mind that the magnetars show no correlation with X-ray luminosities. Here is the conclusion. We can conclude the power density spectra of magnetars is inadequate to make a conclusive statement, and that the power density spectra structure of accretion power pulsars is more comprehensive. In overall, we can say that magnetars' behavior resemble those of the radio pulsars, only that they are more noisier compared to them. And from here, we can conclude that the magnetar model presents a more coherent and viable picture for describing the timing noise of magnetars. And since we did not find a correlation between the X-ray luminosity and the timing noise strength of magnetars, we conclude that the fallback disk model is less likely an opinion to describe the pulse frequency fluctuations of magnetars. And also, depending also when we compare the two methods that we measure the timing noise strength of these sources, we can conclude that the RMS value method is more reliable measurement metric because it measures timing noise on different time scales, and it works both for isolated and binary systems, while the data method gives a rough estimate for isolated pulsars, but is not a reliable metric for persistent accretion power pulsars. This is all I have prepared. Thank you very much.
Thank you very much. So let's answer the questions during the remaining break that we have for like about 6 minutes.
Okay. I will.
Yeah, there are a few questions actually. So you can just read through the chat. There's one from Ali Hoca. How many of your pulsars have disks? And then there's another one about accreting pulsars. What types of accreting pulsars you used? So let's meet for the rest at around 11:30 in order to not.
Can I write the answers in here, or should I?
You can do both. Well, you can do both. However you would like. We have like 5 minutes of